Welcome back, everybody, for this part 2 of our webinar series. This is the final part of Introduction to Population Grids and their integration with remote sensing data for sustainable development and disaster management. Once again, my name is Brock Blevins, Training Coordinator for the ARSET program, and I'll be your host today. Once again, we are joined by members of the POPGRID Data Collaborative, which focuses on different population grids and their application to a range of topics related to development planning and monitoring of the SDGs. Just to recap, this is a two-part training, and this is part 2. All webinar recordings, the PowerPoint presentations, and now the homework assignment is available on the training webpage as you see here. Any questions you have, you can direct them to myself, as well as the NASA ARSET Gmail account. In order to receive a certificate of completion for this webinar series, you will have to have attended both live webinars and submit the homework assignment by April 27th. This is a Google form submission. If you do so, you'll receive a certificate of completion approximately 3 months after the completion of this course from Marinus Martins. Last week in part 1, we had a great presentation from Greg Yetman and Stefan Leik on an introduction to the population data grids, their limitations, their strengths, and their uses. Today in part 2, we're really happy to dive a little bit deeper into how these population grids can be used in different applications, in particular, sustainable development goals and disaster risk reduction. So first, I'm going to send this off to Dr. Robert Chen. He is the Director and Senior Research Scientist for CSUN.
Thanks, Brock. I'm Bob Chen. I am, as Brock mentioned, the Director of CSUN, which is a Center of the Earth Institute at Columbia University. I also am manager of NASA's Socioeconomic Data and Applications Center, one of the 12 distributed active archive centers. And I also co-chair a group called the Thematic Research Network on Data and Statistics, which is part of the UN Sustainable Development Solutions Network. So I'd like to start with just a little bit of history about gridded population data and some of the early applications. I actually started working with our gridded population of the world data set back in the early 1990s when a geographer named Waldo Tobler came to us with this idea of gridding population on a 5-minute long grid to help improve the way people viewed population around the world. Back then, geographic information system technology was just getting started. We, working with Uwe Dijkman, who's also pictured here, pulled together administrative boundaries for about 19,000 units and corresponding populations and created the first version of GPW. The next version of GPW was produced by CSUN, and actually one of the first major applications was to help map poverty and wealth. This was done by Jeff Sachs, who later became the director of the Earth Institute and therefore my boss. He worked to link the population data with estimates of income and wealth and produced this paper that was published in Scientific American. So we have continued to evolve GPW over the years. The version 4 was produced for about 5-6 years ago. And in addition to mapping the distribution of total population, we have made improvements. We've also, of course, increased the resolution and draw on many millions of inputs. But in addition to total population, we disaggregate population by age group and gender. So for example, you can map particular age groups, you can map the difference between males and females and generate a sex ratio as shown here. In parallel with improving mapping of population with GPW, just using better census and boundary data, many groups began thinking about how to model population, and I think this has been discussed more extensively in the previous training session. But just to kind of summarize, from the remote sensing viewpoint, there are a number of data sets that have emerged over the years that have been used to improve the mapping of settlements, of infrastructure and population. So with Landsat, we had 30-meter resolution data with radar on the order of 12 meters. And then, of course, commercial sources of satellite imagery with 3-meter or even under 1-meter resolution. And these allow people to understand where buildings are and associate population with those buildings. And CSUN has worked with a number of groups. For example, a few years ago, we started working with Facebook. And Facebook was actually interested in trying to think about how to improve internet access in rural areas. And they had found that some of the existing data sets which focus on buildings and infrastructure were doing well or better in urban areas, but didn't do as well at mapping population in rural areas. So they saw the potential for processing very high volumes of imagery to do a better mapping in those rural areas. But then as they went along, they also realized how useful those kinds of data could be for applications like vaccination campaigns and other kinds of humanitarian assistance. And they began working with the International Federation of the Red Cross and Red Crescent societies and posted the data openly on the Humanitarian Data Exchange. So those data are openly available, licensed with a Creative Commons open license. So I think you've already heard a little bit about this, so I'm not going to go back into it, but because of this proliferation of different data sets, a few years ago, we decided to develop the POPGRID Data Collaborative, and one of the outputs is this website, which pulls together documentation in a much more consistent and accessible form for all sorts of different global gridded population data. And I think as you have seen in the previous session, we built a tool that allows you to actually compare data for any particular area you're interested in from the different global scale population data sets, including highlighting an area with a polygon or circle and getting the estimate of population in that area. So the main part of my talk, I wanted to give you a sense of the overall different types of applications of gridded population data. You'll hear more in the rest of this session from a couple of people who have worked in more detail on specific applications. But over the years, CDAC, the NASA Data Center, has collected citations on the use of our data. We have an online database which has more than 5,000 citations, and actually over 3,000 of them are citations of the various versions of GPW and another data set called GRUMP, Global Rural Urban Mapping Project. So, and we also track whether these data are used in the same paper with remote sensing data often from NASA satellites, but also other satellites. And about a fourth of those papers cite GPW also use remote sensing data. And we have done on various occasions analyses of these citations. This is from a few years ago. And this pie chart actually reflects not just GPW, but all the data cited in our database. But one interesting thing is just the breadth of applications of CDAX data across the sciences, including a lot in biology and medicine, but also in technology and all sorts of both natural and social and health sciences. So this just gives you a little taste of the breadth of the types of uses of data, at least in the scientific literature. So to give a few examples of the variety, I've pulled some from some higher profile journals. These have both appeared in 2020 in Science. Our GPW version 4 is often used to help characterize, of course, proximity of population to different things, in this case, water bodies, rivers, and coastlines. An interesting one last year, given the pandemic, was it was used to help distinguish location of seismometers, which were being used to kind of detect the change in human activity that reflected in lower seismic noise during the pandemic because of the reduced movement of people. This is a paper that appeared in Nature Communications, which was looking in the context both of natural hazard exposure, in this case floods, and also climate change, and looking at vulnerability now, but also into the future based on different scenarios of future climate change. And then here are a couple applications in the public health arena. Report last year in the Lancet, which actually has higher impact factors than Science and Nature. And in this particular case, it was kind of a broader assessment of health and climate change impacts. And what is noticeable is that in several different health hazards, heat wave exposure, wildfire exposure, and changes in urban green space, the population data is important in highlighting those kinds of exposures and vulnerability. Another paper more recently in the Lancet was looking at helminth infections, and the notable thing about this is they did use the child estimates, the age structure data that we developed for GPW4. So we've seen a number of cases for things like air pollution and other health issues where age is an important factor, and therefore having a better map of the distribution of that age group is useful to those kinds of analyses. So I've focused so far mainly on uses in the scientific literature. Obviously, some of those have practical implications, but we also see gridded population data being used in essentially online decision support systems. So I think many of you may be familiar with the Global Forest Watch, which is available through Google Earth Engine and a number of collaborators. And you will find the Global Human Settlement Layer, which combines our data with work by the European Commission Joint Research Center, as well as reservoir and dam data as one of the layers that is available through that interface. And similarly, there's a website developed by the Partnership for Resilience and Preparedness, which again also brings in population and other layers as an important factor in thinking about climate adaptation and resilience. A operational application of the data is illustrated here in a tool called GeoCollaborate, which has been developed by a private company called Storm Center Communications. They work with a group called the All Hazards Consortium, which helps utilities respond to extreme events like tropical storms and other weather extremes. And in this platform, they don't just show the layer of population if a user wants, but if you can see there's a little square with population on the bottom left, you can actually pull up an interface to make a request to CDAC's population estimation service. And in the interface, draw a polygon or another shape, and then that retrieves data from our server for exactly the geographic area specified. So that allows any user to kind of figure out, well, how many people are in the path of this hurricane or are under a National Weather Service warning area. And that might help first responders and others start to figure out whether how high the risk is and what they might need. This is being implemented now for the National Weather Service and other NOAA centers. That's Dave Jones pointing at the output that his client returns from our server, which again uses GPW as the source of gridded population data that's summed up to the area that a user wants. This is just one example of a different kind of application of our data for educational purposes. Last year, the Guggenheim Museum in New York opened up a large exhibit called Countryside. Unfortunately, it closed within 2 weeks because of COVID and didn't open up till the fall, and then only stayed open until February of this year. But they had a large interactive display with many data layers. You can see our population density in the bottom left, and they have a number of NASA remote sensing layers as part of this immersive exhibit. So my final topic is to discuss really how the population data fits into the larger context of sustainable development. As many of you know, there were 17 Sustainable Development Goals adopted in 2015 by the international community. Many groups are involved. The one I'm associated with, the SDSN Trends Group, has been helping to bring together different communities focused on the intersection of science and development and statistics. The Group on Earth Observations, which is an intergovernmental voluntary organization, early on did this analysis looking at population distribution and infrastructure mapping in terms of their relationship to the goals. And it was pretty clear that population data, knowing where people are, was important to all the goals, not to every indicator, but to many indicators within the larger set of more than 200 indicators that were identified. So stemming from that, NASA funded a set of projects under the Geo-Human Planet Initiative. The one I lead has focused on how population and settlement data can help improve estimation of a number of the SDG indicators. Here's a list of some of the ones we focused on, and try to highlight the issue that countries, in order to develop consistent indicators, need to have potentially population data that is appropriate to the indicators, potentially consistent across the indicators, as well as with other countries. And you will hear in a subsequent talk some of our more detailed work on 911, the proportion of rural population who live within 2 kilometers of an all-season road. And finally, linked with the Human Planet Initiative under GEO, there is a initiative that NASA also helps lead called Earth Observations for the Sustainable Development Goals. They recently worked with UN Habitat to create this toolkit for sustainable cities and human settlements. There's, of course, a lot of our CDAC data, but also tools developed by partners around the world that are helpful or hopefully important for local urban planners and other decision makers at the local, regional, national level to improve not just the indicator assessment, but decision making related to sustainable development. So that's just my quick overview of how population makes a difference, and knowing where people are is critical to a whole range of different applications. This little cartoon from XKCD that some of you may be familiar with kind of emphasizes the point that we mostly care about things where people live, and that matters to us the most. Not that the other planets aren't important, but we are focused on the Earth where we live. Thank you. I'm pleased that following me is Linda Pistolesi, who's a geographic information specialist here at Season. She'll be telling you more, as I mentioned, about the work we're doing with the indicator 9.1.1, focused on rural access to roads. And then later in the session, my colleague Charles Hike from ImageCat, who is partner on our Human Planet project, will be talking more about the disaster risk reduction applications of population and building settlement data.
Okay, my name is Linda Pistolesi. I'm a senior GIS specialist at Season at Columbia University. And before I get going, I'd like to thank my colleague, Season Research Assistant James Gibson, for his work on this analysis and his help with these slides. So this presentation will focus on how population grids can be used with other types of data to monitor progress towards Sustainable Development Goal 9, specifically SDG Indicator 9.1.1, the Rural Access Index. By the end of this session, you will be able to describe SDG Indicator 9.1.1 and how it is measured, identify the inputs used to calculate the Rural Access Index, or the RAI, explain why the choice of gridded population input can lead to different results for this simple indicator, and recognize the advantages and limitations of using currently available open global data sources to calculate the RAI. Sustainable Development Goal 9 aims to build resilient infrastructure, promote inclusive and sustainable industrialization, and foster innovation. As part of Target 9.1, the development of a quality, reliable, and resilient transport network falls under this goal. Good transport connectivity supports inclusive and sustained economic growth and social well-being by facilitating access to local, regional, or global markets, as well as access to social and administrative services. SDG Indicator 9.1.1, commonly known as the Rural Access Index, or RAI, was proposed and accepted as an indicator to measure this target by measuring the proportion of a country's rural population that lives within 2 kilometers walking distance of an all-season road. This distance, 2 kilometers, is estimated as equivalent to a walking distance or a walking time of 20 to 25 minutes, and an all-season road is a road that is passable year-round by typical means of transport. The Rural Access Index was developed by the World Bank Transport Unit and presented in their 2006 technical paper, Rural Access Index, a Key Development Indicator. The report states the Rural Access Index provides a consistent basis for estimating the proportion of the rural population which has adequate access to the transport system. It can help to inform policies and strategies which ensure that the rewards of development are distributed more equitably to the rural population. The report identified two main approaches to measuring the index. The preferred approach was the use of household surveys that include questions about access to transport, as this approach can capture how such access relates to household characteristics such as income and access to services such as health facilities. The alternative was the use of map data, specifically GIS methods and model estimations, to determine the number of people living within the specified catchments of the road network. Based on the methods in this report, the RAI was computed for 173 countries at the national level only, using mainly household survey data. Surveys are costly and time-consuming and conducted about every 3 years, which limits the frequency of RAI updates for monitoring progress. This is particularly relevant at the subnational level because widespread local investment in or neglect of the rural road network can result in more rapid improvements or deterioration at that scale. In 2016, the World Bank published an update to their RAI methodology that takes advantage of the increasing availability of GIS data and technologies, including remote sensing, GPS, crowdsourcing, and open data. This new GIS method is based on 3 sets of geospatial data that provide information on where people live, the spatial distribution of the road network, and road quality. Using the new geospatial approach, the RAI can be computed by GIS software. In place of survey data, the World Bank is now mainly using high-resolution gridded population distribution data developed by the research community to capture where the people are. This is because most countries don't have in-house high-resolution gridded population data. WorldPop's 100-meter gridded data product is the population data set used by the World Bank to compute the RAI. The population data are then restricted to rural areas of national and or subnational administrative units using boundary and urban-rural datasets. The administrative boundary data is always official or national data, while the urban-rural designation is preferentially the national definition, and Season's GRUMP Urban Extents dataset when the national data are unavailable. Digitized road network data are increasingly available from national road agencies, but where a national source is lacking, global public domain and commercial datasets like OSM and DeLorme, respectively, are used instead. Conceptually, the methodology is still focused on access to an all-season road. However, recognizing that not all official road datasets have road condition information, substitutions are sometimes made using technically more objective common parameters, such as roughness of the road, as measured by the International Roughness Index, and the Pavement Condition Index, which is based on visual assessment. The combined road information is used to estimate the rural population within 2 kilometers of an all-season road. These inputs are combined in the GIS software to estimate the rural population with access to all-season roads. This estimate is divided by the total rural population to get the proportion of the rural population with access to all-season roads. The RAI is often multiplied by 100 to present the results as a percent rather than a proportion. The World Bank's geospatial methodology is more cost-effective and sustainable than the original method, as it is no longer dependent on survey coverage and frequency. The geospatial method can also be applied more consistently across countries than the survey-based method, even though the quality of official geospatial inputs may vary by country. This method also allows for RAI estimation at the subnational level, such as districts or villages, which can highlight significant inequality in rural accessibility across areas, aiding prioritization of road improvements and monitoring. Thus, the geospatial RAI has become the most widely accepted metric for assessing rural populations' access to transport consistently across countries and time. The World Bank has computed the RAI for 25 countries so far with this new geospatial methodology. As part of the Human Planet Initiative to operationalize the SDGs, CSIN proposed to use a standard set of global open geospatial datasets to calculate the RAI for every country rather than relying on official national data inputs. The World Bank favors official national data when available, which may produce the most accurate results for the country, but which can limit cross-country comparison and lengthen the frequency of updates. We see several advantages to a global open data approach. The use of common inputs for every country enables better cross-country comparison. By standardizing the inputs, we are able to script the processing workflow, making it easily repeatable with minimal person hours to produce updates. This also supports the possibility of an RAI time series using updated versions of the same inputs. So our model for the global open data approach is very similar to the World Bank model presented earlier. Our inputs are gridded population estimates, national and subnational administrative boundaries and rural areas, and for our all-season roads data, we relied on a single data set rather than separate data sets of road network and road condition, since no global data set exists for the latter. The Python script processed the inputs and calculated the RAI. In the next few slides, I'll discuss the inputs and processing in more detail. Recognizing that there are many gridded population products available to users, we ran the analysis with 3 different data sets and compared the results between data sets. The data products we selected are the Global Human Settlement Population Layer for year 2015, or GHS POP, the World POP dataset for year 2019, or WP, the High Resolution Settlement Layer for year 2015, or HRSL. Each of these gridded population products are produced by members of the POPGRID collaborative, and all the datasets are viewable in the POPGRID viewer shown previously in this webinar. The 3 datasets differ in their inputs, the degree of modeling to produce them, as well as in their cell size or resolution. GHS POP is a lightly modeled product that allocates census population to Landsat-derived built-up areas. It is available at 250 meter and 1 kilometer resolutions. We used the 1 kilometer version. The World POP dataset is a highly modeled product which uses a random forest model and datasymmetric redistribution to allocate census population to grid cells based on statistical weighting of covariate layers such as urban extents, land cover, roads, etc. It's available at 100 meters and 1 kilometer resolution. We use the 1 kilometer version for ease of processing and comparison with GHS POP. HRSL is another lightly modeled product that allocates census population to satellite-derived settlement extents defined by the presence of buildings in high-resolution imagery. HRSL is only available at 30-meter resolution, and while it will eventually be a global data set, it is currently available for only 179 countries. Each of these data sets uses a different methodology to define settled areas and allocate population to those areas. The Database of Global Administrative Areas, or GADAM, is the source for our national and subnational administrative data inputs. GADAM is a high-resolution database of country administrative areas compiled from spatial databases provided by national governments, NGOs, and from maps and lists of names available on the internet, for example, from Wikipedia. Data are available in several formats, including shapefile, and are freely available for academic use and other non-commercial use. By using a standard data set for administrative boundaries, we eliminate the concern for discrepancies between international boundaries that can occur when using official national boundary data sets. The Global Human Settlement Layers Settlement Model, or GHS-SMOD, is the source of our rural areas input. The model is based on population density, counts from GHS-POP, and satellite-derived built-up areas, and provides a standard definition of rural areas across countries. This is important because the criteria used to define urban and rural areas can vary greatly by country and impact cross-country comparisons based on those definitions. The source of our roads input is OpenStreetMap, or OSM. The data are available as global downloads in geopackage format from osmdata.xyz. Using a global roads input provides a common road classification across countries, which supports cross-country comparisons. Since the global geopackage format can be a challenge to work with due to its less common file format and its size, I want to mention an alternative source of OSM data. GeoFabric, a German company that extracts, selects, and processes free geospatial data into more user-friendly formats, provides OSM country-level extracts in the familiar shapefile format. We opted for the osmdata.xyz product for several reasons. To run the analysis globally, and with the hope to complete a time series, the global geopackage extract made the most sense, because we didn't have to download data individually for every country. It also includes all of the geometry and attributes for the primary OSM feature, in our case highways, whereas GeoFabric provides a selection of features and their attributes. The geopackage also has a universal timestamp for the entire global extract, rather than a different timestamp for each country-level GeoFabric download. As mentioned previously, there is no global dataset of road condition information. In order to define all-season roads, we use the F-class attribute in the OSM data, which represents the functional class of the road. While it is more an indication of the importance of the road rather than condition of the road, we use it here as a proxy, as did the World Bank for 3 countries for which they used OSM data. This table shows the 5 OSM F-classes that the World Bank included in their definition of all-season roads for those 3 countries for which they used OSM data. Our visual inspection of roads in imagery during our pilot run with Nigeria, Colombia, and Spain indicated that 4 additional F-classes quite often looked to be in good condition, though there was variability between countries. We decided to expand the definition of all-season roads to include these 4 and ran the analysis with both definitions so we could compare results. Once the full suite of input global open data sets was prepared, we composed a script to automate the RAI calculation country by country. The basic workflow is presented here, though there are some steps omitted for simplicity. It starts with dissolving the global GATM data to layers of admin 0 and admin 2 for each country. Note that the admin 0 layers are used throughout the workflow to make country selections from the remaining data inputs. Here, Nigeria is used as an example. The global SMOD data is converted to Polygon, and only the rural areas extracted for each country. The global roads data are filtered to include only the desired set of roads for the World Bank and season definitions of all-season roads. Then they are buffered, and all buffers dissolved into a single multi-part polygon. This polygon then represents the area within 2 kilometers of an all-season road. The next step is the creation of the zone layers for the zonal statistics operation to estimate the rural population within 2 kilometers of an all-season road. The intersect tool is used to isolate the overlapping features of the admin 2 layer, rural areas layer, and the road buffer layer, thus creating features representing rural road buffers for each admin 2 unit. At this point, a layer for rural admin 2 areas is also created so that the total rural population of each admin 2 unit can be calculated and plugged into the final RAI formula. Next, the 3 gridded population layers are clipped to the admin 0 extent. And finally, zonal statistics are calculated using the admin 2 rural road buffer zones and the gridded population data to get the total rural population in each admin 2 unit with access to an all-season road. To calculate the RAI, we simply plug in the output from zonal statistics into the equation, noting that the total rural pop was also calculated previously. As a proof of concept, Season computed the RAI for Spain, Nigeria, and Colombia using global data methodology just described. The results showed that while the counts of rural population differed greatly, as seen in columns 2 and 4, especially between HRSL and GHS POP, the RAIs were remarkably consistent regardless of the population input. Possible explanation for this discrepancy is that GHS POP allocates population only to areas defined as built-up areas, and therefore tends to underestimate the total rural population. HRSL, by comparison, allocates population evenly to pixels identified as having buildings, regardless of the number or size of buildings. Therefore, it may potentially overestimate rural population or underestimate urban population, depending on the level of detail of the census population inputs. These differences appear to be moot once proportions are calculated, resulting in consistent RAI results. We also tested Nigeria using 2 different OSM road selections and saw the first indication of how different the results could be, depending on which F classes were included in the definition. Adding just one additional F class, unclassified roads, resulted in a difference in the RAI of about 25%. Continuing with Nigeria as an example, here we see the subnational RAI results from our final analysis using the 3 POP layers, GHS, HRSL, and World POP, and the season definition of all season roads in the top row of maps, and the World Bank definition of all season roads in the bottom row of maps. Comparing national RAI results across POP layers, GHS and HRSL produced similar results, with World POP having slightly lower results regardless of the road definition used. However, we can see that spatial patterns, while broadly similar, do have significant differences. GHS and HRSL show greater subnational heterogeneity, whereas World POP results show large clusters of admin 2 units with similar RAI values, particularly in the World POP results computed with the World Bank roads definition in the bottom right. This feature of the World POP results may be a consequence of roads being included as a covariate in the model, and therefore more population being allocated to areas with high densities of roads. As with the pilot work, we see that using a more inclusive definition of all season roads produces RAIs that are consistently 25 percentage points above results obtained with the less inclusive World Bank definition, regardless of the population layer used. Just to note that in this slide and all the other maps in this presentation, gray units had either no rural population with which to calculate the RAI, or the RAI results were greater than 100, which is an error. Looking at the national level RAI results using the more inclusive season roads definition, we again see relatively similar patterns regardless of POP input, but more quantitatively similar results for GHS and HRSL as compared to World POP. The same similarities hold true for national level RAI results using the more restrictive World Bank definition of roads, though overall the RAI results are lower. At the subnational level, using Africa as an example, here with Season's more inclusive roads definition, we see a rather dramatic difference between the World POP results and the other 2 datasets, especially in areas of the Sahara. These lower RAI values are likely due to the World POP model, which does not predict 0 population values in any pixel. Rural areas with population in administrative units are assigned a small per pixel population estimate, This adds up over large, likely uninhabited areas like the Sahara, resulting potentially in overestimation of the rural population without access to roads. The spatial patterns in the Africa subnational RAIs using the less inclusive World Bank roads definition show similar spatial patterns to the previous maps. And as with the Nigeria and national examples, the RAI values are consistently lower. Looking at the preliminary global average results for our RAI analysis, we see that Season's more inclusive selection of all-season roads results in global average RAIs that are consistently about 10 percentage points greater than the averages computed with the World Bank definition of roads. This indicates that a better understanding of the correspondence between OSM F-class and road condition, as well as a better global road condition dataset, would help the analysis. For both definitions of all-season roads, GHS and HRSL averages are generally consistent with each other and about 8 percentage points higher than the World POP results. This is consistent with World POP often predicting lower RAIs for a given unit, likely due to the manner in which the model allocates population in large rural areas. We are still working on this analysis and waiting for final results for some countries, and hope to conduct more assessment of our results against the current World Bank results. As we come to the end of the presentation, I would like to discuss some limitations of the global open data approach. With regard to gridded population datasets, there are several to choose from, each with their own biases and frequency of updates. With regard to the global boundary dataset by GATM, the boundary resolution and quality varies by country, and its handling of disputed areas is not transparent. In addition, the update schedule for GATM is unpredictable. But despite these issues, at this time, GATM appears to be the best open global national boundary dataset. With regard to defining rural areas, SMOD may not align with the national definition of rural areas, which are used for policy and resource decisions. And in terms of roads data, as a crowdsourced data set, OSM quality and coverage can vary by country, especially in rural areas. The dataset also has limited road condition information, and using the F-class as a proxy requires further refinement. Finally, the dataset is not associated with government responsibility, and therefore can't really be used for prioritizing road improvements. In the global approach, the accuracy of the RAI ultimately depends on the quality of the OSM roads data for a given country. Let's review. SDG indicator 9.1.1, the Rural Access Index, or RAI, measures rural access to all-season roads. RAI can be effectively calculated by combining geospatial data for administrative units, rural areas, roads, and population. While there are advantages to using global datasets, such as standard inputs, automation, and temporal comparisons, there are also limitations. The choice of POPGRID dataset and OSM road selections significantly impact RAI results calculated using this method. But ultimately, this is a simple and effective method for monitoring RAI globally. For this presentation, we access the following references as well as, and we've included the data sources here as well. Thank you very much for your attention. I'd like to introduce the next speaker, my colleague Charles Hike from ImageCat.
Thanks for joining me today. I'm Charles Hike from ImageCat. I'm going to be talking about work that we do there using population data to develop building exposure databases for the purposes of looking at the impacts of disasters. This work has been funded through a number of research grants, primarily recently through the UK Space Agency and their International Partnership Program, Project Meteor, led by British Geological Survey. There's been a number of rounds of funding from NASA Disasters Program, including one now looking at critical infrastructure, and of course the Human Planet Project that we've been working on with CSUN. So in this presentation today, I'll assume that most of you are coming to the table with minimal experience with the subject, CAT modeling, and loss estimation, CAT standing for catastrophe. So I'll give you an introduction of the area, try to give you an understanding of what the data sets are used for, what the accuracy of the data sets is, and then give you an understanding of the value of EO data in this process, and understanding, once the results are developed, what the uncertainty is that's inherent in the results, and what the appropriate use of those results are for decision making. So loss estimation, or catastrophe modeling, is the process of estimating what might happen given a certain excitation from a natural disaster. So if you've got a hurricane, tornado, earthquake, we predict what might happen before an event. So for example, if you were to look at large earthquakes that might hit Los Angeles in a planning capacity, during event, as it sort of unfolds. So this would be in circumstances like where you have a hurricane approaching the coast, and you want to understand what the evacuation might be, or what the staging resources might be, given different instances of how landfall might occur. And then on average, so using what's called an event catalog, looking at thousands, sometimes millions of events, trying to characterize everything that might happen and how likely we think that might be to happen. So many storms, many fires, many earthquakes, looking at on average what happens in any given year. And that can be used for cost-benefit analysis purposes to evaluate the cost efficacy of mitigation options, for example, or it can be used to price insurance, or to understand relative risks of various hazards, and so on. So first, taking a look at what building exposure for DRR, or disaster risk reduction, is. Most of you are familiar, I'm sure, with these type of renderings, architectural renderings of buildings that are used for multiple purposes, from entertainment to planning and so on. This is most decidedly not what we're looking at when we're talking about building exposure data. What we're talking about really is a very specialized product that's used in conjunction with what we call hazard and vulnerability data to be able to find the risk of a given hazard throughout an area, or a given peril throughout an area. So in this context, the hazard is the manifestation, or the potential manifestation, of the natural hazard that we're looking at, whether it be flood, earthquake, wind, tornado, sea level rise, coastal hazards, or whatever. The vulnerability in this context is what we sometimes refer to as a damage function, which will indicate what the likely damage to a given asset or infrastructure asset is given that hazard. So for example, how much damage you would expect to have from a house if it had a foot of water in it versus 2 feet of water in it versus a wave hitting it, or what have you. The damage can be expressed in terms of a percent of the total value. It can be expressed in terms of a dollar value for estimated repair cost, or it can be expressed in terms of days down, or potential cascading impacts that might have. But in all these circumstances, you have to have an understanding of the exposed assets, that the assets exposed to the hazard and the vulnerability. That's why we call it exposure. And in this context, what we are talking about is an estimate of the building exposure, as opposed to populations, vulnerable populations, critical infrastructure, or what have you. So we're really talking about the built environment, and more specifically, buildings themselves. So here's an example posted by the GEM Foundation, that's Global Earthquake Model Foundation in Italy, that produces open models, earthquake models for the entire world. They've served the data that we've come up with in the Meteor project, which is data for about 47 countries. And here you can see most of Africa and a gridded data set there that's at the 15 arcsec resolution. And for each grid cell there, if you click on it, you get the answers up here on the right, which is essentially what the value of the exposed buildings are in dollars, what the area is in square meters, what the building count is, of course, what the location is, and then how those assets, those buildings, break out by construction type. And here we have some codes which map to specific vulnerability functions or damage functions that will estimate, given amount of peak ground acceleration typically, or ground motion, what they expect the damage to those facilities to be. So for example, here we've got W, that's simply wood frame, and then several other codes that map directly to construction types. So very specifically, what's in these building exposure databases is the number of buildings, where, by type, and cost for the purposes of estimating vulnerability and hazard proximity. So here we have four very different types of buildings that you would expect to find in four very different locations that are more or less resilient to various hazards that might be in their environment. So what we're trying to figure out is, given all these four types of buildings, which ones are most vulnerable to wind, earthquake, flooding, and then under those conditions, what you can expect to have happen regionally to get a dollar value for, say, disaster response, mitigation, a real-time action, and so on. So how we develop these building exposure databases, in the first place, we collect census data, the most accurate census data that we can, given the level of detail justified by the project. So if you can get a microcensus data, if that's available, that's wonderful. Sometimes we go to a country and get the census data that's available from them, download it on a vector basis, and oftentimes we just default to a land scan or a world pop database. So within the census, we look at the census data to see if there's any indications of building construction patterns. Sometimes there is, sometimes there's not. But the next step is to essentially estimate the building attributes shown in the previous slide. How are people living where? And to refine the spatial distribution. So this is the sort of dimensional mapping process that WorldPop might do when taking census data and disaggregating it to a grid basis. We need to do that as well, but taking into consideration the building types themselves. I'll talk more about that later. Estimate the number of buildings. That can be as simple as looking at the number of people and the number of people per household and estimating the number of households and then estimating the number of buildings from that. But you can also adjust that regionally based on what building patterns that you're seeing in an area. And then last is to estimate the replacement value, which can be quite difficult given development practices in various countries and even what's meant by replacement value. Essentially, the damage functions themselves, or vulnerability functions, will give you an estimate of the percent damage typically, and you multiply that replacement value. So what your client, what the end user wants that replacement value to be, whether it's depreciated to current value or takes into account permitting or architectural costs, is essentially up to them. But regardless, what we come up with working with folks is the estimated replacement cost per square meter that we multiply out by that, ultimately that estimated amount of building stock. And in there, between those two phases, of course, is estimating the average square footage of each of those buildings, and that too can vary by the types of areas that you have. So drilling down into each one of those steps with a little bit more detail, estimating building attributes. We start with a literature review of the predominant building construction types for a country. Sometimes there's reports specifically for this type of application that have been written. Google, just going to Google Scholar or World Housing Encyclopedia from ERI is a great resource for this. USGS Pager has sort of a first guess for the entire world. Interpretation of EO data right off the bat, taking a look at what the patterns, the development patterns are, how those look by different sort of types of land use that you can see in high resolution satellite data, for example. Expert opinion, depending on how much detail and money you have to develop a specific country or area of interest building exposure data. You might interview many experts that would be able to inform typically how buildings have changed throughout the last couple decades, and you can use that in conjunction sometimes with EO data to characterize different vulnerability patterns and different building patterns. Virtual reconnaissance, this is the process of really looking at a lot of street view data where that data is available. It's very good for engineers to drill down. And even if you don't have street view data, you can have in situ photographs, tourist photographs, all that type of stuff that do capture buildings will allow you to get an understanding of how buildings are made in different environments. And if you do have a budget that will justify it, site surveys and stratified sampling. I'll get into the idea of the strata a little bit later, but looking at different development patterns in urban environments, rural environments, single-family environments, if those are around, and figuring out what the typical breakout of different construction patterns for each of those types of environments can be done through a randomized sampling process, which we like to do if we've got budget for it. And then lastly, again, the housing census, sometimes separate from the population census, will have in many countries, whether you have what the roof, wall, and ceiling materials are, and from that you can often infer the construction of the building. Another important step is estimating the number and size of buildings by development pattern, or sometimes a region of the country. This is simply the process of taking the estimate of how buildings are made and what you can see in the EO data and how many people there are in a given area, and then estimating from that what you would expect the number of buildings and ultimately the size in terms of square meters of building area. Livable building area that you would have, and that typically varies by something we call development pattern, which I'll get into a little bit later. But urbanity, rural, urban, and so forth. So people per household and households per building, as I discussed later, is the simplest way to do it. But that often leads to a lot of error, particularly if you only have a number of people per household at the national level. It can vary significantly based on even in the rural environment in a given country, depending on cultural differences or climate differences and this type of thing. So being able to calibrate that, your estimate of the number of buildings and the size of the buildings with building footprint data is very useful. If you've got OSM data, for example, you can take samples of that and estimate your building counts. Count the buildings, footprints available in the imagery, and then compare that to your estimates. That's a great way to calibrate it, and you can again do that against other types of EO data, for example, SAR data, and then use that SAR data to estimate number of buildings and or square meter coverage directly from that attribute. Microcensus or government reports will often give you more detail on number of households per building that you can adjust regionally if you can't get that in the raw census data. A distribution of building area by story height. So this is story height might not be something that you can directly get from EO data at the level that we're really talking about it. We're not talking about developing per building data here. It's aggregate data. But you can come up with a distribution perhaps from the sampling process or a interpretation process, and then from that estimate the total building area. And of course, these things vary by population density, as I said, urbanity, or EO metrics like the SAR will sometimes correlate highly with these attributes. So estimate of replacement value. As I said, this can be a little ambiguous in terms of whether you depreciate the data or what's included in the replacement value itself. But even a crude estimate can be very, very difficult to gather. And believe it or not, this is an area that we found that EO can be quite helpful. So there are international guidebooks in terms of how to do this. We've got some of them here. SPONS, for example, is a very popular one. There are estimates that are available globally. For example, what GARC has put together on global damage functions. Their document has an estimate based on simply on GDP alone as a function of GDP, which is a nice sort of first guess. But what we find is that the value really, the replacement cost value really varies by the rigor of construction. And the rigor of construction itself can often be guessed or characterized by development patterns in the EO data. So if you've got rural areas, you often have much less rigorous construction, what we would call temporary housing or semi-permanent housing. And in the urban areas, you're much more likely to have permanent housing. So that alone can be a very strong indicator of what the replacement cost is. We've found that resettlement action plans that are available, that's essentially if they're building a roadway or a big dam and they have to acquire property and have people move out of the way for them to build that infrastructure. They've got a negotiated price that they will pay for those properties and the relocation, and we find that that's a very, very strong indicator of what the replacement cost is, and allows us to essentially characterize the replacement cost of those less rigorous temporary housing as a percentage of the permanent housing in the country. So estimating replacement value is an area that's often sort of overlooked. But it's if you're off by 50%, which is I think pretty easy to do, then your loss estimates are going to be off by 50%. Because a direct correlate to your answers, and there's a lot more room there than in the damage function. So these, in terms of the absolute value, not the distribution, but in terms of the absolute value, can really impact your results. All right, building vulnerability attributes. So these are the attributes of the buildings themselves that can be directly mapped to a damage function that allows you to estimate the damage given, say, depth of flooding in meters, as we've got here on the right. So this is an example of various damage functions based on for flooding based on different rigors of construction. Here we just have abstract names, but the one that's on the top there, you would expect to see more damage, and so it's a less resilient structure than you've got on the bottom, the purple, which would have at 1.5 meters of flooding an estimate of 40% damage. So these can be extraordinarily rigorous. There's tens of thousands of combinations of them that have been put together to estimate what the damage what the vulnerability for specific buildings are. Obviously, when you're putting together a building exposure database for the national level, for example, you wouldn't have that much detail. This is a detail that's more suitable for if you are having an engineer go out and look at specific buildings or even designing specific buildings. But you kind of do what you can, and you pick through and you figure out what you think is necessary. Here are some of the things that people consider era of development. This is particularly important when you're looking at countries that have rigorous building codes and adhere to those building codes and the codes have changed throughout the decades based on often significant events. So for an example, in the United States in the Southeast, you've got residential construction changing in terms of its vulnerability to hurricanes significantly following significant events. Number of stories is a key value in terms of the resonating frequency of ground motion for earthquakes, or in terms of the wind profile. First floor elevation, that's how much that first floor is above ground level. If you've got a crawl space in there, for example, or if you've actually built the building with what's called freeboard, or built it on stilts to avoid flood, that's a very important metric for flooding. The basic construction materials, lateral force resisting system, that's for earthquake. Whether something has been retrofitted, nail density is a big one for hurricanes, which obviously you can't see from the sky. So what the best you can do is be able to tie these back to things that you can essentially see and characterize regionally. If you've got specific data, as you often do for the United States, you can use that. But for EO-based exposure development, looking particularly for the international community, what we can do is essentially come up with development patterns, characterize where you have what types of collections of buildings, and then take the key salient exposure building characteristics from those and be able to characterize the percentage of buildings that are in each of those bins. And typically what you want is between 5 and 10 combinations of all of these categories. It's very easy to get more combinations of these construction types than you do buildings, which can be quite problematic if you're trying to distribute them and figure out what the losses are. So it's a constant balance between engineering rigor and reasonable statistical practice, but we do what we can. So hopefully that sets up the problem pretty well. Finally, we get to the directly to the subject of what role does EO play in all of this. So first of all, those global population data sets, particularly internationally, are very important, because then we can just sort of piggyback off of all of the great work that others have done on trying to dimensionally or realistically estimate populations, and then use that as a starting point to estimate the number of buildings. Global urban / rural or urban intensity data sets that are starting to come together, like GUF and GHSL and so forth, are very useful. We'll get into that in a little bit. Next, segmentation of development patterns. So what we can do is try to look at sort of the texture, if you will, of buildings in a given area to infer not necessarily land use, but building pattern extraction. So where you've got different types of building patterns corresponds pretty directly, depending on the country, to the way that people are building buildings. Building footprint extraction to get the estimate of the building area, average building size of that. And then another area that's exciting is looking at AI from things like video, people trying to extract things like window area, presence of soft story buildings, first floor elevation, and various attributes from directly from street-based video data, or ground-based LiDAR instruments, or UAV data, or these type of sensors. Basically allows you to sidestep the process of conducting a survey and directly take those attributes from data that's collected on the ground without having that engineering experience on the ground. All of this is pretty much, I would say, in its research phase, but promises if we're able to harness that type of ground-based data, then we can combine that ground view with the sky view, if you will, to develop building exposure databases. So building footprint extraction, most of you are probably familiar with this technology, and you're probably familiar with how it often doesn't work. You can try to square off buildings. Sometimes you get more buildings than you anticipated. And trying to make sense of that can be problematic. But I would posit for this application, where you don't really care how many buildings you have, the number of buildings, as much as you do the square footage of those or square meters of those buildings, because that's what directly correlates to the replacement cost and the ultimate damage. What you get from EO data is very handy. That said, it's a pretty intensive process in terms of area. You don't typically get it for very wide areas, at least when we do this type of work. We use it often in terms of a sampling technique, but with the Bing data sets and the Facebook HRSL data sets, it's now becoming more reasonable to apply that nationwide in certain circumstances. So that's quite exciting. What you need to watch out for, however, is that when you don't have that data, for example, in India, we were looking at the HRSL data, and we did not have it for Calcutta, I believe, but we had it for the rest of India. And it's very easy to aggregate that data up or make assumptions with it, and then forego one of the largest cities in a country, and then have a very skewed look at risk. So whatever you want to do, you want to make sure that you sample from a statistically robust perspective, if you don't have it for everywhere. And even if you do have it for everywhere, you have to make sure that it's that you're comfortable that it will do consistently well everywhere. But that being said, it's a very, very good resource to nail down exactly how much building value is exposed. So this is more typically how we use it, not for an entire country, but looking at specific areas, just going through and extracting the building count and building area for different types of construction in different types of development patterns in different types of countries. So, you can understand certainly how this rural residential, high density residential might be easy to distinguish in remote sensing imagery. And then once you have those areas, being able to have an estimated count, average square meters, and total building area by multiplying by the number of average number of stories in those types of grids would really work for sampling strategy when you're trying to infer the number of the ultimate building area from the population. So the process of establishing these development patterns and then extracting them through segmentation is really quite iterative, and works better in some places than others. So this is a nice crisp example, I guess I would say. In China, you had mid-rise residential construction, which all looked a specific way until a certain date where it all looked a different way. And you could really tell by the density of these mid-rise residential structures and the heights, and you could really look at the difference between these, the 6-story buildings and the 12-story buildings, for example. But for each of those, you can have an engineer establish what the construction pattern is in those areas, or what these buildings are made of, and map that directly to a vulnerability function. Now, they're not usually this clean. You don't usually have one building pattern or one building type per development pattern. Usually you have an array of them that you'd characterize. But this illustrates the process of having engineers look at what's on the ground and talk to the remote sensing folks to figure out what they can reasonably extract, what you can see in the imagery, what you can't, and then sort of triangulate in on what's a reasonable development pattern to have for your area of interest, which we typically establish at the country level. So here's an example of what that looks like for a small chunk of Beijing. You can see from the shadows a pretty consistent building and elevation for these dense residential areas. And it's clear to see where you've got some of the older parts of the city that's all low rise, as well as the intersecting industrial buildings and infrastructure and what have you. So we run our classification algorithms over there, and as you would imagine, they're not perfect, but they're okay. This is the result of running the analysis at the pixel level, and I believe this is Landsat data or moderate resolution data, and you can see quite a bit of scatter in the initial classification, and then what we do is aggregate that up to a larger scale where you've identified, you filtered out some of that noise and identified from a statistical approach what the development pattern is, and then you can start to associate with each of those what the breakout of building types would be. So the question of which to use of those last two slides, for example, the higher resolution data or or an aggregated form of it is a big sort of question, and I think it depends largely on what peril you're looking at and how you're using the data. So if you're giving the data to a client, aggregating that data up where that noise is sort of smoothed over, if you will, at the cell level, and the numbers you're working with the law of large numbers, and you're more likely to be accurate in terms of a given 100 meter or 500 meter square area, how many buildings that you would expect to be in that area. You're going to be much more accurate for that than you are going to be at the say 15 meter level. That being said, if your peril is highly localized, such as looking at landslide risk, coastal risk, or riverine flood risk, for example, having that higher resolution data and maybe not posting the number of buildings at that cell level, but using that as a basis to statistically internal to the program estimate what the losses are, I think can give you a more accurate result, because in these circumstances, location is everything, probably even more important than the structure types. So if you've got the sinuous rivers, as you actually do running here, you're not going to be pixelating them. You will have a little of that apparent noise visible, but you'd be able to identify with more accuracy, if you've got an inundation area, what the expected surface area of, in this case, Beijing, you would expect to be covered by that peril. So this is a little bit of a detail that I think that this crowd could probably appreciate more than most. But it has a lot. It's a big question in terms of sacrificing the accuracy of what you post and put out there versus the accuracy of the result that you get from the model. And just to sort of complete the story here, this is for another country, but for each of those colors that you're able to, or these development patterns that you're able to identify, was in the colors in the last maps of Beijing, you're able to map that back to specific distribution. So I made the example there of the mid-rise residential structures in China, but this would be more what you would see from a development pattern typically, which would give you, the percentage of buildings that you would expect in a cluster of maybe 5 to 10 types. So here we've got steel high-rise on the left, steel mid-rise, going down to steel low-rise, then reinforced concrete mid-rise, and reinforced concrete low-rise, and moving to the right to all the way to stone, snow, mortar, and URM stands for unreinforced masonry. So you can see, as you've got these rural and residential greens and blues, you have quite a bit more over here to the right, which is less rigorous construction. And as you have these reds, oranges, and yellows, you have more of the steel frame and reinforced concrete structures. So this plays out for each of those cells to be able to classify and break out the structure types into these classes for the purposes of the vulnerability functions. Really gives you a much more accurate estimate of what your losses are. So the question that most people have, or they should have after hearing this pitch, if you will, is how good is this stuff? You know, particularly if you've got people that are thinking about, well, we've got building specific data, why not just use that? Well, you don't typically have building specific data for an entire country. Sometimes you do, and then in those cases, maybe you can use that and buy that. But even under those circumstances, you're going to have error associated with your model. And it's important to understand what the uncertainty is based on that, that's introduced by this process. I would say traditionally, in the field of exposure development, particularly in the United States, people have said, well, you've got the law of large numbers working in your advance. And the law of large numbers is, you know, you may be a little off here and a little off there when you're looking at particular assets, but on average, you should zero in on a pretty good representation of the overall situation. But that simply doesn't account for bias, right? If you've got error in terms of individual interpretations of assets, that's probably pretty good. If you're trying to estimate what the total building value of buildings in Tanzania is based on average people per household data that you've got one number for the whole country, then you've got significant bias, and you're going to be off in those types of calculations. So one of the things that we tried to do on the Meteor project is to come up with various levels of building exposure database to characterize how the buildings were developed to communicate, and then after that to assess what the uncertainty was by running all of them through a full probabilistic model for Los Angeles, which we had in our back pocket, and see what the uncertainty is. So really quickly, these 5 different levels. Number 1 is a global level. You can consider this like the Landscan or WorldPipe type of database. Level 2 is a national database. In this case, it was a HAZAS database, which uses all federal level data. A level 3 is improved national level data, considering regional adjustments to key indicators. You can see it's a little different than 2. That's where we used some of our EO secret sauce. Level 4, you can immediately see it's almost as if the exposure comes into focus. That's where you skip to building specific data that's actually aggregated, in this case, up from Microsoft Office building footprints. And level 5 is where you've got building specific data itself and run all of that through the data. In this case, it's a Los Angeles County tax assessor data. So what we're trying to say, this is called an EP curve. And on the bottom here, we've got years of a return interval. And on the y-axis, we have the dollar value in loss, essentially. What nobody knows is how much inherent exposure data or error is there in the process of developing exposure data. As a rule, you use the best exposure data that you have, and you develop the best database that you have. Nobody had really compared different methods of developing building exposure data and looked at the amount of uncertainty introduced by that building exposure data process itself. People look at a lot at various hazard data sets and vulnerability curves and the impact of those, but exposure was not looked at in such a rigorous manner. And what we found was not entirely surprising. The spread in the various databases that we put together for Los Angeles was about a factor of 2, a little more than a factor of 2. But the interesting thing is that it didn't sort of monotonically increase towards the middle or the top or the bottom. It was not a matter of the more accurate data that you integrated into the process, the more accurate of a result that you got. So for example, here level 5, which is that Los Angeles County tax assessor's data, is on the bottom. And level 4, which is with Microsoft building footprints, is on the top, with the level 3 in the middle being the stuff that we did with the EO data. A little above that is the HAZUS data, and then level 1, which was the global data, down there by the Los Angeles tax assessor database. So the as we drilled down into those different answers and had some independent review from engineers, we did a sampling to figure out what we really felt like the risk was and what the answer should be. And what we found was it was right there in the middle, about level 3. But the factors that were resulting in the distribution that we saw were all attributable to key factors that in the end affect the dollar value per the dollar value of the area. And these are very, very simple. I've said them all already here before. The persons per household, the living area per household, the rebuilding cost, and then, as we've seen internationally, exchange rates, which didn't apply to Los Angeles, but it's been a very important one. The focus, I think, is often on vulnerability or geographic resolution of the exposure data sets, but these key factors, and I could go through, if you're interested, contact me, of each of those 5 and iterate why there was a considerable variation. Just one highlight: the Los Angeles County tax assessor data was systematically sort of underestimating the building exposure value because they don't have government buildings, for one. For another Prop 13 law here, where in California, where we don't reassess the billing value for tax purposes unless it changes hands. So these kind of systematic biases can really affect your final results, even more than the data that you use from a geographic standpoint. So that being said, bringing it back to the population data sets directly, here's some research that was done by Cascade Tucholsky, looking at the exposure of various population data sets to ground motion. It's called quake intensity down here. It goes from 6.5 to 8.5. And if you look in aggregate at the population exposed to each of the bins in here, you'll see that it doesn't vary that much over the level of about 7.5. And if you were to look at the aggregate results, this is a case where the law of large numbers really does probably wash out the differences in the results. I'm sure that if we tied a loss model to this, and I would like to work with Cascade to do that, we would find variation that was far below the 2.5 that we found for a probabilistic loss analysis in Los Angeles, even though these results might look quite different. And the folks in the audience that might have been involved in putting these together would be surprised to hear me say that. But because the vulnerability, particularly in this case, might not vary significantly throughout the area, these results are, as a person involved in loss estimation and CAP modeling for 25 years, does not surprise me, and I would be very satisfied to be able to have these type of answers come back from an international event and use that for decision making. So in essence, this does get back to the nature of the peril, however. So if getting back to the more accurate aggregated results that you might have are nice for earthquakes and hurricanes. The higher resolution for floods, landslides, it's probably much more appropriate. But again, that's difficult data to distribute because at the cell level there might be just so much variation, and people would be very tempted to repurpose that data. So having that built into a model might be a more reasonable way to use it. So this brings me to a very important point that I constantly have to sort of reinforce. you can't, you have to address expectations of the client. This data cannot be used to accurately estimate the number of buildings at the cell level. Can't capture very small regions. It can't capture things that remote sensing can't capture. Settlements are always a challenge, and so forth. And to a certain extent, you have to take pause and remember what you're trying to do. If you ask the question, how much does it cost to build this hut, for example, on one level, the answer might be nothing, right? Because this is all indigenous materials, and probably nobody was paid for the labor. So you have to make sure that that what you're characterizing is equitable and answers the questions that you're wanting to prioritize in a given disaster risk reduction effort, and that is often the number of people exposed and the disruption that you would anticipate, whereas the dollar value might not be a very good indicator of that. You have to make sure that that the amount of buildings exposed or the square footage exposed to a given hazard and what the looking at how that might disrupt the population itself has to be considered along with the dollar value. Okay, real quickly here at the end, because I've gone on a little bit too much. Inappropriate uses, is it cost effective to retrofit specific buildings? Which buildings are going to fall down? Exactly how many buildings are going to fall down? These are not the type of answers that this type of data can adequately reflect. What it can do is tell you, is it cost effective to retrofit certain types of buildings? What might happen given a 100-year flood or a large earthquake or volcano, or something has just happened? Where should we be sending resources? Where should we be checking for damage and casualties? Where should we send our search and rescue teams? These larger picture issues are much more appropriate.
Thank you very much, Charles. So what we're going to do now is we're going to move right into the question and answer session. So please type your questions into the Q&A box. Some of the questions that have been asked so far throughout the presentation today, we've been moving over to a Google document, and we will start working our way down through those one by one. Okay, welcome to the question and answer session. We have been diligently trying to address these questions as we've been going along, and we have all the trainers on here to help us out with these. If we don't get to your question, please feel free to email me and I can try to redirect that to the trainers on today, but hopefully we can get to them all. So I'm just going to start off, and who is most appropriate to answer the questions, please feel free to then unmute and hop on. So question one, do we have older age, over 65 years, population of the world, especially India, as a population grid data?
So we do have older age gridded data, as long as there was such an age class in the census inputs. So we're available. We gridded the data at 5-year age groups up to 85 plus. So we do have data available for those years in GPW4, and WorldPop as well has global age and sex data in 5-year age groups.
Great, thank you. Yeah, and I will post these links into the question and answer, or excuse me, the chat box there. And of course, we will have this available for download with all the links and references available on our training webpage in due time once we sort of clean it up a little bit. But I'll post these here if you want to, so see the chat for those links. Question two, how did you validate the demographic data with GPW?
I'll take this. There's some text that shows a method of how we took the age category proportions and applied them to the 2010 estimates. So these are really estimates. The age totals do add back up to the national level world population prospect estimates, but there's no real detailed validation. And that's a general issue with all of the population estimates, GPW and others, which is that these are model estimates of population distribution. And it's actually quite difficult to do what you might consider a full validation, that is comparing the estimates with actual, detailed location data for specific households and that have specific demographic characteristics. Those data are very difficult to obtain for the scale we're talking about in all the different countries. They're obviously in private and confidential in terms of the willingness of census agencies to share that data. So those kinds of detailed validation studies are difficult, and I don't think any data set has been fully validated from that viewpoint, although many data sets do attempt to see how their models compare with data on the ground.
Thank you, Bob. Question 3, and some of these earlier ones came a little early.
Did we send that?
So number 3, are these methods available in R for spatial disaggregation of counts?
Again, maybe.
Sorry, Bob, go ahead.
Go ahead, Linda. No, I was going to pass the buck to you.
Okay. So, well, I was just going to say that I personally don't work in R, but yes, there are methods available in R to do this type of work. I believe the WorldPop random forest algorithm is written in R and uses, the packages available there. I don't personally have experience with R, though.
Yeah, we can try and tap one of the other people who may have better knowledge about it to provide some more details.
Yeah, we'll try to throw a link in here before we post to the training webpage. That'll be great. What is the best population data set out there suitable for flood mapping in urban coastal cities like Accra versus flood mapping in island countries like Mauritius, which consist of both urban and rural areas? Looking for some key limitations to consider when using the public data set for both cases.
So I'll take a stab at that. There's not a simple answer. Even the same data set may have different quality based on the data that they use for a particular country or region. Actually, I think the example that Charlie gave done by Cascade Tucholsky, looking at the risk differences, indicate that if you're at a high enough scale, the data sets may produce similar results. But as you drill down, it's a little hard to tell which is going to be better. We are in the middle of a study that's looking at slum areas, and we are starting to find that actually all the available data sets may be underestimating the number of people actually in the slums. But again, you have to take that with a grain of salt, because the validation data for slums is itself got problems and issues regarding those counts. So we did produce the publication that's available on the POPGRID site to try to give guidance on issues and limitations, which can cover a range of factors about the different data sets. And we do encourage people to use the POPGRID viewer to kind of give you a sense of what the variation is, and that can maybe help you judge as to whether a data set really is appropriate for your application in your particular area.
Great, thank you. And question 5, it looks like maybe we needed a little bit more expansion on this question, but the question was, what data should I use in a project that involves tea production management?
Yeah, and I wrote this initial answer. We'd need more specifics about what the question is. I could imagine that if you're looking at, say, who's affected by tea production or pollution, you'd want data that looks at those areas and does a good job kind of capturing the residents involved or living in the exact area. But if you're looking at markets, you might want to know something about the demography and the type and economic level of populations in cities near there. So it's a little hard to judge what data is appropriate for the project of interest.
Great, thank you. And question 6, it looks like this user is already working with some WorldPop data. So I'm currently using WorldPop raster data to assess the population impacted by gully erosion in urban areas of the Democratic Republic of Congo. I've noticed that in large cities, the population pixel values are highly differentiated, which is good. While for small affected urban areas, is the opposite, and the population is grossly underestimated. Is there a way to overcome this problem?
I think James and I both wrote a bit of a response here. So it's not clear, how the person who wrote the question was addressing how they determined that there was this huge underestimation in the urban areas. But there are other, the best suggestion would probably be to experiment with some of the other data sets, maybe starting with looking at the POPGRID viewer, in those areas and seeing how the other data sets are representing the POP in those urban areas. WorldPop provides their data both unconstrained and constrained. Constrained means that they are using a settlement model and only allocating population to areas that are considered settlements, whereas the unconstrained version is allocating population, without the incorporation of a settlement model. And so, both of these may have different results for how much population is being allocated to urban areas. GHS POP also allocates population only to satellite-derived built-up areas, which may result in more population in those urban areas. So just sort of comparing those different data sets and how they're representing the area that is of interest would be the main suggestion here.
I guess I'll weigh in on this one because I've found this to be true. Really, the question. It's important to recognize that these are global scale data sets, and when you're doing a more localized study to look at populations affected, for example, by flooding, I think it's important to adjust and come up with your own answers that identify those smaller settlements that are difficult to characterize with moderate resolution data. So it's a great place to start, but if you're looking at a specific area, adjusting it is what you typically need to do.
Thank you. And question 7, kind of a technical question here. What is the GeoPackage format? And what are the merits and demerits, I guess, limitations and strengths?
James, maybe you want to chime in since you have the most experience working with that for our project?
Yeah, so I wrote this little answer. I worked with GeoPackages for the project that Linda presented on the RII. So it's like another format for transferring geospatial information. It's like an SQL format, so if you're familiar with that, it's pretty easy to use. In Pro, I found it was a little bit difficult to work with, but they can contain like tons of data and tons of information, which is really great. And I just added that you can work with them in Python using the GeoPandas package. So that can also like help in making it just more like easier to work with.
Thank you very much. Question 8. How do you delineate urban and rural areas? Is there a global acceptable definition for urban and rural areas?
So I can field this one. James and I both contributed to this response, but there isn't currently, I guess, a standard that is adhered to by all countries, although there is a proposed and accepted by the UN standard for degree of urbanization, and the description is there in the response. But generally, every country has their own way of defining their urban and rural areas, and so this is an issue for indicators that are based on urban-rural delineations. It affects the way that we can compare each country's results and progress towards the indicators. So that's why global settlement models like GHS SMOD, which we use for the global RII, are helpful because they take a standard approach to defining urban and rural areas globally based on pop counts, densities, and satellite-derived built-up areas. And the SMOD approach, or the methodology used to produce SMOD, does actually follow the degree of urbanization method, although the final product is provided at a sort of more refined level. So there's not just urban and rural areas, or not just limited number of classes, but I think there's something like 8 or 13 classes in the SMOD data set, and they can be aggregated to that degree of urbanization one using the outline in the dataset documentation.
I'll just add, as I just typed in, that the accepted degree of urbanization approach was actually developed by the European Commission's Joint Research Center, which is our partner under the Geo-Human Planet Initiative, and uses the data that was developed jointly between JRC and CDAC.
Great, thank you for adding that as well there, Bob. Question 9, what does the UN adjusted world pop dataset mean? Are there other population datasets also UN adjusted?
So UN adjusted means that the population totals in the grids. So when we first produce the grids, we check the population totals for every country against the official UN national totals reported in the World Population Prospects, which comes out every 2 years. And based on our totals versus the UN totals, we calculate an adjustment factor that is then applied to the population estimates in each grid cell so that the national totals in the final grid match the UN totals. And so not all grids are adjusted in this way to match the UN. Both GPW and WorldPop provide the population grids either adjusted or not adjusted, and it's usually explicit in the data set name whether you're downloading a UN adjusted data set or an unadjusted data set. The unadjusted won't usually say unadjusted, it'll just say population counts or population density. But if it's been adjusted to the UN totals, it will be explicit in the name.
And just to clarify, there are differences in the national totals because the census data that all the georeferenced population data sets are based on may not correspond to the UN year, and we have to do simple extrapolations to get the data to be consistent. And those adjustments mean there can be differences between what the UN population prospects thinks is the national total and what our data say is based on the original census data. So that's where you get why you get differences that need to be corrected.
Great, thank you. Question 10, do you have any examples of using gridded population data to assess damage, disaster damage or risk, and its impact by gender?
I guess maybe I'll go ahead and start with this one since it was asked during my session, although I'm not sure my answer is the best one. For the analysis that we typically do, we use demographic data to estimate what's going on with buildings. And then once we analyze what's going on with buildings, we sometimes then look at things such as casualties and injuries, and that can be applied back to the impacts to populations in general. So it's not used directly in the assessment that we've done, although sometimes afterwards, if you look at things like building damage and gender ratios and working relationships and so forth, people do use that to make conclusions for response. But it's not something that I've seen done directly a lot at the development phase. And I guess there are some examples on CDAC if someone wants to take that part of the answer.
Right. I put that in. I just, one of the things that I'd like to see more of is people using the citations database to actually try to find relevant information for questions like this. So if you actually go to the database and you can see which entries cite a particular data set. So you can actually click the GPW version 4 collection, and then within that pick the two data sets, revision 10 and revision 11, of basic demographic characteristics that has the age and gender breakdowns for 2010. And when you search on that, you actually find 15 citations. And the database doesn't contain the full paper. It only contains the titles and basic citation information. But reading it, there's like 4 or 5 papers that specifically mention heat waves, tornadoes, floods, air quality, and COVID. So I don't know if the papers actually look at a gender. You'd have to read them, but at least it gives you a starting point to find out if anybody has actually done a detailed analysis of gender using these, disaggregated population data.
Okay, question 11, and looks like this is about exposure data, so possibly this is for you here, Charlie. Is there a foundation of buildings considered to come up with the building exposure information?
Well, as I expressed, you can develop the building exposure data at many different scales, but for this sort of aggregated view in general, you sort of want to get the factors that are most directly applicable to the peril that you're trying to analyze. I have seen, frequently first floor elevation can be very important when estimating damage from flooding. So in that case, the foundation is considered a bit. But for earthquake hazards and most flood applications, what you typically see is people looking at the roof material, floor material, roof material, wall material to infer a structural class. And it can be it's used in the context of that, but typically not directly. Some folks that are doing more detailed analysis will try to infer what's called secondary indicators, which can include foundation type if they've got a damage function that directly relates to it, but in general, it might be too much detail.
And question 12. Is there the real Earth surface slope land cover considered to buffer the distance of 2 kilometers of all season roads? And it looks like this is for you, Linda and James.
Sure, so I'll take it. There isn't currently, well, we didn't use that for the global analysis because there currently isn't a global road condition data set, which is what getting at the real Earth surface, you know, the road condition information is what is trying to get at the real Earth surface to determine whether the road is, you know, passable all year round. So we just use a buffer distance and try to get at this question of all season roads using the F-class attribute in the OSM data as a proxy. And that really needs a bit further refinement. The F-class attribute can vary a lot, you know, country to country. Or how it's been applied can vary a lot, I should say. The attribute itself is, you know, has a definition, but how it's applied country to country can vary. So this is part of the global analysis that could be refined.
Great, and before I move on to question 13, I just want to mention a couple things. I know we're at the top of the hour. We can take a couple more questions and then address the other questions offline and get this posted in the future. I really leave that up. I want to be respectful of everybody's time. So if there's trainers that need to drop off, that's understandable. If any of the participants want to drop off, you have other things to do, please feel free. I also want to note that the homework is now available under part 2 on the training webpage. That is due by the 27th of April. It's a Google form submission. As I mentioned, if there are trainers that need to drop off, go ahead, but maybe we'll take just a couple more.
Yeah, Brock, I think most of the rest of them are for me. I can take the, I can stay on.
Sure, yeah. We'll we won't go too much past the hour, but let's address a couple more of these audibly. So question 13, can a type of dwelling unit be used as a proxy for poverty levels in developing nations?
You know, I thought this was a great question. We generally sort of think of it, I think, the opposite way. When we look at these development patterns, you can definitely see what we call the durability of the structures. Which is a direct correlate with poverty, which you know, we use that to estimate the fragility of the structures as well as the replacement cost. But we haven't thought about using that as a direct indicator of poverty for other purposes much. That being said, on the Human Planet project, we have started talking with through the introduction of Bob Chen to a group. They're called idea maps. Is that right, Bob? That is starting to look at the characterization of deprivation areas. You know, and in that specific case, we think that there might be quite a bit to contribute. So we are sort of looking into that, or beginning to look into that, and I think that there's a lot of potential there.
Great, thanks, Charlie. 14, which resource do you recommend for imperviousness density and how to obtain it from any US environmental.gov agency?
Bob, you want to take this one? I guess there is some data on the CDAC site.
I'm sorry. Yeah, I wasn't totally clear if the person was looking for impervious surface area. There was a study done a few years ago by some NASA Goddard scientists using Landsat data to model impervious surfaces as a factor in also defining urban areas. So that data set, GMIS, is available on our site at that link. It's actually an interactive viewer, so you can visualize and download the data since it's at 30-meter resolution.
Great, thank you. Yeah, and that surface area, impervious surface area data set also applicable to SDG 1131. Question 15, are these algorithms open code? If yes, where can we access them? And I'll post this URL in the chat.
Yeah, we are a commercial company, so we don't publish our algorithms. That said, it's really more of an art than a science. Each project, really requires its own assessment of the area that you're developing at the scale that, what's changed. Things change quite quickly in terms of data availability and so on. That we also try to make it very clear what we do and how we do it. We're very transparent in that regard with the metadata, so that people can go in and update or augment the data for their own purposes. But yeah, I would recommend anybody who's interested to really check out the Meteor project, where we've got 47 countries worth of this data to download and play with.
Great resource to have. Question 16, how can we identify persons in a household through EO data?
Yeah, I mean, really the reason I keep focusing on the persons per household is because it's, in most cases, what you're doing is you're going from a population estimate to an estimate of the number of households to the estimate of the number of buildings. So obviously persons per household is a key determining factor. You can't actually infer that from the EO data itself, or I don't know how to do that. But you use that in trying to estimate how many buildings that you're going to effectively spread. And then when you check that, you can check that with other data sets that are EO based and figure out where your answer is wrong, where you don't have essentially enough buildings based on either what you've been able to extract with building footprints, and then you essentially adjust after the fact.
Great, so question 17, as buildings are very heterogeneous in nature and their unit replacement costs varies a lot depending on spatial location, what do you think should be the factor delineating the areas that can be considered to have similar unit rates for replacement cost?
Yeah, I could talk about this for several hours. So I think that the important, I mean, it gets to the nub of the matter. I think the important thing is to keep in mind that you're really trying to characterize the majority of buildings. If you have too many forks in your statistical model, that to break out from each individual cell, for example, then you quickly get to a condition where you've got more forks than buildings. And when you start to run a Monte Carlo analysis, for example, you're just generating noise. So I always sort of think if there's less than 5%, it's not worth characterizing. And if you've got any sort of special structure in terms of a sports stadium or elaborate mosques or these kind of things, it's important to, if you do address them on a point basis. So hopefully that answers the question. Feel free to reach out to me if you'd like to discuss it. It's an excellent question.
Question 18, my question is, how do we deal best with different resolutions of ancillary variables vis-a-vis population gridded data?
Yeah, I don't think there's any easy answer to that question. It's just basically it's a data fusion process. Anything that you've got in terms of observation or microcensus data, you have to be very careful to integrate in a way that you don't introduce any sort of bias. If you have detailed data in one location but not another that's very similar, and you integrate it for the place that you have the data, then you're going to come up with an answer that skews your answer of risk either towards or away from the other community, and in a disaster that's going to affect the distribution of aid. So you need to be very careful about it. And what we found is using these sort of similar development patterns is the best way to assure that you don't do that or guard against it.
Great,
And
thank you.
Bob, I added a sentence because I'm not totally sure what the person means by dealing with the resolutions. It's really, from our viewpoint, the issue is the gridded population data based only on, say, census doesn't give you a good understanding of population spatial variations at really fine scales. So the ancillary data that's available at finer scales is really the tool by which you try to infer or model those variations. Now, hopefully that they add useful high resolution information that improves your estimates. There's no guarantee of that. So, what Charlie just said about it being an art and needing to be adjusted based on the development pattern, I think is really useful. But it's really a feature of what we're doing, of trying to meld data of different resolution and scale to make a better estimate that's useful for researcher applications.
Great, thank you. So we have 2 questions left. I think we can get through this one. And really, the number 19, is there data available for island on Haiti? And it looks like the link here to the Meteor project is here, and that there is data available. So I'll just move on to question 10. I just want to make sure I correctly understand. One can simply add its own particular data to POPGRID and perform analysis. One could exchange data, let's say replace WPP data with their own personal estimates.
Oh, I'll take that. So I wasn't sure if the person, since I didn't talk about it briefly, but it was talked in the first session, the POPGRID viewer just allows a user to draw a polygon or a circle or some other area, and then for that area just get what the total population is in that area for all the different georeferenced data sets. So it doesn't allow any further analysis. If someone has their own census data and wants to grid it, they would at present need to, put that in a GIS and apply an algorithm. Or I think it was alluded to before. Are there tools in R and other languages to do gridding? Those are available, but there's no online service to do that. Although we've actually talked about it and thought about what other functions one could perform over the internet, such as letting people upload data and then using the population data to help them create weighted averages, those sorts of things. But at the moment, all one can really do is get a custom estimate of extract of the population data summed to a user-defined area.
Great, thanks, Bob. That's a good clarification there. So that brings us to the end of our Q&A session, and it also brings us to the end of our 2-part training. So I'll have this video available for you to review on your own time within about 24 hours. And the homework, as I mentioned before, is also there. And we'll get the Q&A docs up, all cleaned up with the appropriate links as soon as possible for you to use as a resource. So I just want to say to Linda, James, Bob, Charles, thank you very much for this Q&A session here today and for part 2.
Thank you.
Thanks, Brock. Thanks, everybody.
Okay, great. Have a great week. Thank you.